Hey, welcome. So today we're going to crack open something you probably see every single day, the humble thermos, or as it's officially known, the vacuum flask. It looks so simple, right? But inside this thing is an absolute masterpiece of physics. So let's get right into it and uncover the incredible science that keeps your coffee piping hot.
I mean, that's the real question, isn't it? You pour in a hot drink, screw on the lid, and hours later, it's still hot. It feels like some kind of magic trick, but I promise you, it's all pure, unadulterated physics. And to figure out how a flask traps heat so well, we first have to understand how heat is always trying to escape.
You see, a thermos is basically designed to fight a constant battle. It's up against three invisible enemies. These are the three fundamental ways that heat energy moves from one place to another. Let's meet the culprits.
Okay, first up, you've got conduction. Think of it as heat moving through direct touch, like particles bumping into each other in a solid. Then there's convection. This is how heat moves through liquids and gases, like hot air rising. And finally, there's radiation. This one's different. It's heat traveling as invisible infrared waves, kind of like the warmth you feel from the sun. It doesn't need any stuff to travel through. So these are the three escape routes for our heat, and we have to block all of them.
And that brings us to the most important thing to understand here. A flask doesn't make anything hot or cold. It's not a heater or a fridge. Its one and only job is to be a heat transfer minimizer. Think of it as an insulated fortress, specifically designed to slow down heat's escape by blocking conduction, convection, and radiation.
So how in the world does it actually do that? Well, let's pop the hood and take a look inside. We're going to deconstruct this thing to see exactly how this incredible heat trap is built.
This is probably the best way to get a mental picture of it. It's not one single container. It's a double-walled structure. You've got an inner bottle that's literally nested inside an outer one. And the real secret, the absolute genius of the design, lies in what's, or maybe more accurately, what isn't, in the space between them.
So here are the key players in this operation. You've got the two bottles, that all-important vacuum gap between them, these really shiny silvered surfaces, and of course the stopper on top. Each one of these parts has a very specific job to do in our mission to stop heat from getting out. All right, let's start with the flask's absolute #1 weapon, its secret sauce, the vacuum. This is that almost nothing I was talking about, the empty space that sits between the inner and outer bottles.
And this is where the design gets really clever. Both conduction and convection absolutely need particles, molecules, to transfer heat. Heat needs something to travel through. So, by sucking almost all of the air out from between the two walls to create a vacuum, you've removed the highway for heat to travel on. With almost no particles in there, there's no bumping for conduction and no currents for convection. It is a brilliant 2-for-1 solution that just shuts them down cold.
And just like that, bam! 2 of our 3 heat loss enemies are basically defeated. They're stopped dead in their tracks. But there's still that third one, the one that can sneak through even the emptiest of spaces. So what do we do about that?
This brings us to the second line of defense in our thermal fortress, and this one is all about tackling that final, sneaky form of heat transfer, radiation.
So remember, radiation is heat traveling as waves. It doesn't need air or any other medium to move. It can shoot right across empty space. That means our amazing vacuum is totally useless against it. The heat from your hot coffee can still radiate right across that empty gap.
So, what's the solution? Well, it's brilliant. You coat the walls facing that vacuum gap with a super shiny, mirror-like silvered layer. You see, shiny surfaces have what's called low emissivity. That's just a fancy way of saying they're terrible at giving off heat, but they are fantastic at reflecting it. So any heat waves trying to radiate out from your coffee hit that shiny inner wall and get reflected right back in. It is literally a mirror for heat. And it works the other way too, reflecting outside heat away from a cold drink.
Okay, so we've got the walls totally secured. The vacuum handles conduction and convection, and the silvered surfaces deal with radiation. But we've still got one really obvious vulnerability, right? The big hole at the top where you pour stuff in and out.
In any great defense, there's always a potential weak point. And in the vacuum flask, it's the stopper. This is the one place where the inside world has to make physical contact with the outside world, creating a potential bridge for heat to sneak across.
This is why the stopper is engineered to be as defensive as possible. It's usually made from a really good insulating material, like plastic or cork, which are just awful at conducting heat. It also creates a super tight seal, which stops hot air from escaping through convection. It's really the final piece of the puzzle, sealing the deal and locking that heat inside.
Okay, so the defenses are amazing. We've got a near-perfect vacuum. We've got reflective walls. We've got an insulating plug. But, as we all know, your coffee does eventually cool down. So why isn't the Flask's defense absolutely perfect? Let's put this all together.
Okay, so here's the big picture. The whole system works together as a team. The vacuum completely stops conduction and convection from crossing that big gap. The shiny silvered surfaces bounce that pesky radiation right back where it came from. And the insulating stopper does its best to plug that final escape route at the top. It is an incredibly efficient system.
But, like I said, it isn't perfect. And the main reason for that comes down to a fundamental engineering problem, something known as a thermal bridge.
Think about it. The inner bottle and the outer bottle have to actually connect somewhere, otherwise they just fall apart. They're usually joined together at the neck of the flask. Well, that tiny point of physical connection creates a path, a little bridge, for heat to slowly, very slowly, conduct its way out. It is the one unavoidable weak point in the armor that ensures, over a long period of time, heat will eventually escape.
So, just to make sure we're all on the same page, let's bust a few common myths. First, a flask doesn't add any energy. It only preserves the energy that's already there. Second, a vacuum does not stop radiation. That's what the reflective walls are for. And finally, you can't just rely on the vacuum. The vacuum, the silvered surfaces, and the stopper all have to work together. It's a total team effort.
And there you have it. The vacuum flask isn't just some boring container. It's a precisely engineered system designed to outsmart the fundamental laws of thermodynamics for as long as it possibly can. It really makes you wonder, doesn't it? What other everyday objects that are sitting around us right now are hiding equally incredible science just waiting to be discovered?